Okay, good morning, guys. So I owe you some explanations. Since you're here, I assume that you've seen the Canvas announcement. Give me just 1 second to switch things over. Go. So, after Wednesday's lecture, one of my students, one of y'all, reached out to me and let me know that in their previous class, they had heard about an issue or experienced an issue with WebAssign and HonorLock not communicating with each other. Because of the way I had WebAssign configured for my classes last semester, I never ran into that issue. My students were able to take tests just fine with HonorLock in WebAssign. But the way I have them configured this semester, it is not the case. So either something weird happened in the development team with HonorLock, or the development team on WebAssign, maybe they changed their API, I don't know. But for whatever reason, WebAssign and HonorLock are no longer friends. They don't talk to each other, which means if you were to have tried to take the exam the way we talked about it today, everybody would have run into issues, would not have been able to get in. And so we have to reconfigure the exam, that's all. I'm going to reconfigure the exam to take place in Canvas. And HonorLock works great within Canvas. There shouldn't be any issues. There was another way to go about it, using a shell quiz in Canvas to then send you over to WebAssign. But that looked a little bit complicated, and I don't want to change the directions last minute and then have you not have time to internalize those changes before the test. So the test has been pushed to Monday. And it will be in Canvas instead of WebAssign. Canvas does have like a little equation editor that will allow me to type mathematical questions in a quiz. So I'm going to take a format of an exam that I've used in the past and do my best to implement that format in Canvas. So for gradebook reasons, I don't want to try and inject the questions into the existing gradebook element titled Exam 1 in Canvas. That's going to stay there. And that is still where you're going to submit your written work after you finish the test. But the test itself is going to show up in Canvas under the Quizzes tab. So I will post an announcement with very detailed instructions, making sure you know exactly where to go. But in short, there's going to be a Canvas quiz titled Exam 1 or Test 1 or something like that. And it's going to have like 5 true-false questions. So under quizzes, there will be about 5 true-false and about 5 multiple choice. And these will be graded automatically. You don't need to show work. Or scan anything for those. I mean, if you have written work for them, then you're welcome, of course, to scan it and submit it along with the rest of the written work that you will be submitting. But the idea is that these get turned around immediately for you, and I don't need to grade them. They're just done. There will also be somewhere around 7 free response questions. Canvas calls these essay questions. And here's how these will work. So in the Canvas quiz, as you're working through the test, These will be questions that have fairly simple final answers, right? Where you can type the final answer without too much trouble. And that's what I want you to do as you take the test. So you're going to work the problems on your own paper, neatly, nice organized work, and you'll enter your final answer in Canvas as you take the test. And then after you finish, you will scan your written work and submit it under the exam 1 assignment. The idea there is that you'll tell me what your final answer was in the quiz, and then you'll show me the work that led you to the final answer in your scans. And that way I can be reasonably confident that the work that you submit in your scans is the work that led to the answer you gave. So you'll type your final answer as you work the test. And then you will scan and submit the written work immediately after you finish the test. So what I don't want anybody breaking out their phone to try and scan and submit work while they're working the test. That is obviously an academic integrity no-no. And I need some way to be confident that the work you're scanning and submitting is related in a meaningful way to the answer that you gave during the test. So having these 2 different points where you're submitting responses for each of those questions allows me to verify that. I don't think this is horrendously complicated. I don't think anybody will have an especially hard time with it, as long as you have played around with the scanner app on your phone. So make sure you do that. If you don't have one yet, please download it now. iPhones, you can use the Notes app, apparently. I don't have an iPhone, so I'm not sure. Android, I really like Cam Scanner. It's worked well for me, but there are several others. There's one called Tiny Scan that is okay, and you know, whatever you want. But yeah, you'll go through. The quiz will be in Canvas. You'll answer these true, false, and multiple choice questions. You don't need to stress about having perfect, neat work for those because I won't be grading the work for those. And then you'll answer the free response questions. So if each free response question, you're going to want a sheet of paper. You'll work the question very carefully on that sheet of paper. Once you get to your final answer, you will type that final answer into the box on Canvas and then move on to the next question. After you've finished the test in Canvas, or the quiz in Canvas, you'll submit, you'll say, I'm done with this, submit it, and then immediately scan your work and submit it to me in the assignment titled Exam 1. And again, watch for a Canvas announcement showing up this weekend with like the exact names of the places for you to go, the exact links for you to click, but it should all be pretty intuitive. And Nicholas asks a good question. Is there any partial credit for the true, false, and multiple choice? So first, let me give you the scoring breakdown. The true, false are worth 2 points each. The multiple choice are worth 3 points each. And the free response are worth 5 points each. There absolutely will be partial credit on the free response. That's the idea. I think in the time I've been teaching, I have maybe twice given partial credit on a true, false, or multiple choice question. And this was a case where somebody had a lot of written work on the test and they'd circled the right answer, but then scratched it out and circled the wrong answer, but then scratched that out and circled the right answer, and then scratched that out and circled the wrong answer. And I could see from the written work that they were very, very close to having the correct answer. I don't expect to be giving any partial credit on the true, false, or multiple choice here. Like I said, in all the time I've been teaching, there have been a few exceptions, but no, as a rule, no, I don't give partial credit on the true, false, or multiple choice. But I do give very generous partial credit on the free response. Of course, these won't be graded immediately like those will, so these guys will give you a reasonable feel for how the test went, and then I will grade these. It'll take me probably about a week to get everything turned around, and you'll have the full final grade at that point. So yeah, that's how it's going to go. It's going to require me to finagle the gradebook a little bit, so if you notice things changing in the Canvas gradebook over the weekend, please don't panic. And I will post a final announcement sometime over the weekend explaining exactly what things to click and exactly when. If you have testing accommodations through the DRC, then these will need to be reconfigured. So I did reach out to the DRC last night as I was working on this shit, just to warn them, to let them know, hey, the test is not tomorrow. It's going to be moved to Monday, and it's going to be moved to Canvas. But if you had planned to have them proctor you with Zoom or anything like that, we may have to change those arrangements a little bit, because I don't know how well the Zoom proctoring will work within the Canvas shell. And I'm also not sure if I can build in a workaround for honor lock in the Canvas shell. So the workaround, if you're going to use Zoom through the DRC to proctor, then that would have been easy. I would just give you the password for the exam in WebAssign, and you never have to launch honor lock. But here, an honor lock proctored quiz within Canvas, as far as I know, there are no extant workarounds. So I will spend some time on the phone with the DRC and with the honor lock people and try to find a workaround. But just be aware that you may have to use honor lock. We may not have the option to have the DRC proctor through Zoom here. If that would be a problem, let me know, and we can talk about it and try to find some sort of compromise or workaround. But from what I've seen so far, I think it might be the case that there is no possible workaround. But I'll work with you. I'm sure the DRC folks will work with you. Honor lock people have been pretty helpful. So if you have any concerns about anything like that, just let me know and we'll figure it out, I promise. I think that's everything I wanted to say about this. It should be pretty clear. So Monday, instead of a regular lecture, we're going to have the test. It's going to be in Canvas. You're going to go to the quizzes to find it. And then after you finish the whole quiz in Canvas, you will take your work for the free response questions, scan it, and submit that work under the assignment titled Exam 1 in Canvas, just like you were going to if the test had been in WebAssign. One, I guess, other little thing, I want to make sure I did this. So I'm going to change the due date on homework 5 and the study guide to Monday. Yeah, I haven't done that for you guys yet. So let's do that now so you can continue using those to prepare for the test over the weekend. So this is now due on Monday. The procedures for the study guide haven't changed at all, just the due date has. So you'll still need to complete this assignment in WebAssign, scan and submit your work in Canvas. And of course, I encourage you to email me little bits of that as you go so I can give you some feedback. I know that there are a few folks who have done that already and are waiting for a response from me. Yesterday, when I learned about this honor lock bullshit, it consumed my whole day trying to get it fixed. So I'm sorry I haven't been able to reply to those yet, but I promise I will do so today. So still a good thing to do. Come by office hours or send me pictures of your work or whatever so we can talk about it and I can give you some feedback before the test. Any questions on the structure or procedures for exam 1, how things are changing? Okay. So a few questions here. Thomas asks, kind of how will the true-false questions look? Usually, the true-false stuff is like, I'll give you a statement and ask you whether it is true or not. So I would say like, true or false. If you make this substitution in this integral, the result is this. or true or false. You know, the integral of 1 over x squared plus 1 is the natural log of x squared plus 1, that sort of thing. So they'll be fairly straightforward, usually concept type questions that you can answer quite quickly without doing a lot of calculation. That's the idea behind the true false. My true false do have a reputation for being a little bit tricky, but as long as you are comfy with the concepts that we've talked about, they should not overwhelm. The multiple choice questions will be brief calculation questions. So like, which of the following is the correct partial fraction setup for this function? Something like that. Those are the flavors of multiple choice questions I use. And then Dalton asks, does the test end at the end of class? I'm going to use the same testing window thing that we had set up for WebAssign. So there will be a 2-hour window beginning at 11:30, during which you can take the test in Canvas. But then once you begin the test, you'll have 75 minutes to finish it. So if you start right at 11:30, then your test will end when class ends. But if you start at 12, then your test would end 30 minutes after class ends. So there's a 2-hour window during which you can take the test, but the test will be time limited to 75 minutes, unless there's something else that we've talked about, like accommodations through DRC. And then Nick asks, oh yeah, sure, Nick. Yeah, if you want to come through the office hour and ask a quick question at the start, that's fine. I'll watch for and admit you first in the waiting room. Okay. Other questions about the test procedure or how things are changing or what it is you need to do? Okay, then the rest of the class, I'm happy to spend working some more review problems with you guys. Or if you're bored with review problems and you don't want to do any of that, I can start introducing some of the material we will talk about after exam 1. It is exciting stuff. It is fun stuff. It is not super easy. So it's up to y'all. Are there any problems lingering from the homework or study guide that you guys would like to talk about today, since we have this extra day before the test? Anything like that, just go ahead and type it in the chat. Some trig integrals, 13a from the homework, 8 on the study guide, 9 on the study guide, 18 from homework. This looks like a good start. Okay. So let's begin in homework 5. (13, 18, and 9. So I'll go in numerical order here. Number 9 from homework 5 is the first. Oh, wait. Do I really want to do this? Number 9 is a long problem. We did start it the other day, and I don't remember whether this was the one I finished or whether it was the one above, but I can give you a start here. Yeah, no, I mean, today definitely wasn't supposed to be a review day. Today was supposed to be the test, but we had this weird technology conflict between WebAssign and HonorLock. Okay. So let me write this down, and then I'll flip back to the dot cam. I think so too, but it was requested, so I'm going to give just a quick tip on how to get this going. The trick here is trig sub, but before you can do the trig sub, you need to write that square root as like the square root of u squared minus a squared, or u squared plus a squared. You need to make it look like something from our trig sub table, the little trig sub Bible we have. And the game there is completing the square. So I did post something to the Canvas modules last week on completing the square, or earlier this week, I think. So do take a look at that. Basically, we're going to add and subtract some number under that square root such that if you group the first three terms together, they will factor as a perfect square. So if you haven't seen that, that thing in the modules, I'll show you here quickly. I think it's under trig sub. Yeah, resources right down here. So take a look at this document here. You can download it. I would recommend downloading it and viewing it in your own PDF viewer. I might even have it open here. My shit's fucking up for some reason. Yeah, here it is. All right. So you may want to download this and look at it in Adobe or Sumatra or whatever you use to read PDFs. But we talk about how to complete the square. We use it to prove the quadratic formula, which is fun. If you've never seen the proof of the quadratic formula, it's right here. It's not hard, and it's all completing the square. But then I do some examples and solve an integral. So this is the trick. We're going to add and subtract 1 underneath the square root, and then this piece factors as x plus 1 squared. So that makes my integrand look trig subby, which is my goal. So I get x plus 1 squared minus 1 under here. And then from there, you can either substitute x plus 1 equals secant theta, or you could do a little u sub first. Since every other time I've done this, I've done it the other way. Let me go ahead and do it this way for once. So I substitute u equals x plus 1, du equals dx. This becomes integral square root of u squared minus 1 du. And then we do the trig sub, which for this guy would be u equals secant theta. Du is secant theta tangent theta d theta. And we can draw our triangle. Secant is the hypotenuse over the adjacent. So that's u over 1, and that makes this the missing piece, the square root of u squared minus 1. So there's the trig sub. And when we plug those things into the integral, we get secant squared theta minus 1 under the square root, and then secant theta tangent theta d theta for the differential. Secant squared minus 1 is tangent squared. Square root of tangent squared is tangent. So this is tan theta times secant tangent, which is tan squared theta times secant theta d theta. And this is where I will stop, because from here, this is a looping IBP problem. It is not easy. It's time consuming, and we did it on Wednesday. So if you want to see it, feel free to go back and watch the video from Wednesday. If you don't want to dive in and do the looping IBP directly, you can convert this into an integral of secant cubed and secant. Tan squared, remember, is secant squared minus 1. We used that earlier. So this is secant squared theta minus 1 times secant theta d theta. And if you distribute this secant over that difference, you will get secant cubed minus secant. So an alternate approach, if you don't want to do the looping IBP directly from here, would be to come down here. Because some people do memorize the integral of secant cubed, it might be a faster path. But this is as far as I want to go on this one today. If you want to see the full solution, take a look back in Wednesday's video. So the next one that we wanted to see study guide, 13A from homework, 9 from homework, 18 from homework. All right, 13A in the homework, we can take a look at that. Yeah, this is also one that I think we've done a little bit of. Basically, we need to do the long division here. The game will be I want to find the PFD setup for the function x to the 4 minus 2x cubed plus x squared plus 2x minus 1 all over x squared minus 2x plus 1. So let me write this down. There we go. I can't begin with the PFD because the degree of the top is not strictly less than the degree of the bottom. Right? The degree of the top is bigger than the degree of the bottom, so this is improper. So what we need to do is begin by long dividing, and then we'll see if there's some PFD we can do. So long divide the top by the bottom. So to do that, I write the denominator x squared minus 2x plus 1. And then over here, x to the 4 minus 2x cubed plus x squared plus 2x minus 1. And then my division bar. We pay attention just to the lead terms. So by what must I multiply this in order to get this? So to get x squared to turn into x to the 4, I need to slap him with another copy of x squared. And then I distribute that x squared to everybody here, and I write down the result underneath this. So that's going to be x to the 4, that's by design, minus 2x cubed. So that's going to be nice, plus x squared. And then you can think of this as plus 0x plus 0, or some people just say you bring down the stuff over there. Either way is fine. What you got to do then is subtract the rows. So subtract the bottom row from the top row. X to the 4 minus x to the 4 is 0. Negative 2x cubed minus negative 2x cubed is 0. X squared minus x squared is 0. So what do we get? I've got 2x minus 0x, that's 2x. Got minus 1 minus 0, that's minus 1. And now just like in grade school when you were learning to long divide, this is your quotient, this is your remainder. Which means that my function can be written as x squared plus 2x minus 1 over this denominator, x squared minus 2x plus 1. So depending on who you took pre-calc with, you may or may not have gotten a lot of practice at this, but I hope by now we're getting more comfy. There are a few things that I posted under the review material resources in Canvas that will help you get comfier with this if you are not yet comfy with it. It should be up here at the top. Yeah, right here. So this guy, and this guy are all about dividing polynomials. In any case, to finish the problem, we need to factor that denominator. So PFD setup is, I've got my x squared, and then this plus 2x minus 1 over that denominator. That denominator factors, though. That factors as x minus 1 quantity squared. And so if I had to set this up as a partial fractions problem, this guy is just coming along for the ride. It would be a over x minus 1 plus b over x minus 1 squared. And this is what WebAssign is looking for, I believe. Any questions on this fella? Yeah, I see how the format of this and part B from the first problem can be a little bit confusing because you have to do the long division first, so it's not 100% clear whether you just want the PFD part or whether you want the whole functions equivalent. But yeah, this is what we're looking for. So was there anything else from the homework? Yeah, 18. Let's take a look at 18. I don't remember what that was. Nick, I want to give a good answer to that, but I'm not 100% clear on what the question is. So anything that isn't a part of the fraction after you divide it out is just left aside. Yeah, so I think I follow. So this guy doesn't need any PFD stuff because he's a polynomial. The PFD is only for the rational function bit. So because he doesn't have a denominator with factors, there's no decomposing him. But this guy does have a denominator with the factors x minus 1 repeated twice, so he does need that. So the x squared comes along for the ride because there's no need to decompose him, and then this guy gets decomposed like that. Yeah, if I had gotten a larger quotient here, then that whole quotient would be here, and then whatever remainder term would contribute the piece that still needs decomposition. Okay. 18 is not too bad. There is a meaningful chunk of PFD to do here. Write it down as it is with the numbers. (17 over x minus 1 times x squared plus 16 dx). All right. So like the last guy, this is a PFD thing. I do have this irreducible quadratic factor downstairs to contend with, so the PFD setup is slightly more complicated. And the Heaviside trick will not get everything for me, but it will give me a little bit. So I set up my PFD. I know that this quadratic is irreducible, for example, because I can picture the graph, right? The graph of x squared plus 16 is the regular x squared graph bumped up 16 units, which means that it will not have any x-intercepts. No x-intercepts means no factors, because a factor and an x-intercept come together. So this guy really is irreducible, which means that the setup looks like this. I'll give an a over x minus 1, and then a bx plus c over x squared plus 16. And then I clear the denominators and get ready to do whatever Heaviside stuff I can. Here the x minus 1's cancel and I just get a times x squared plus 16. Here I remember to put my bx plus c in parentheses because of course the fractions are grouping symbols. The x squared plus 16 cancels and I get x minus 1. If you plug x equals 1, then the second term here goes to 0. So here's the Heaviside trick. We get 17 equals a times 1 squared plus 16, which is the same as 17 equals 17a. So a is 1. Now, I have two little secrets that I want to tell you that I'm not supposed to tell you, but I'm going to tell you anyway. First, if you are comfortable with complex numbers, then there is no such thing as an irreducible quadratic. Every polynomial factors over the complex numbers. The roots of x squared plus 16 are plus and minus 4i. And I could plug in 4i for x here and make some shit drop out. Trick 1. Trick 2, this line should be true for every number x in the universe. You can plug in whatever the hell you want. It's nice to plug in things that make a bunch of shit go away, but that's not the only option. I could plug in x equals 0 to this line, and even though it won't make everything go away except for one constant, it will still give me a true statement. So if you don't like multiplying everything out and equating coefficients, you can get some equations to solve for b and c by plugging other numbers in for x here. Plug in x equals 0, plug in x equals 1, plug in x equals 2, plug in x equals -1. If you're feeling sneaky, plug in x equals 4i. All right, so I said that just for fun. Let me show you what will happen if I plug x equals 0. I'll get 17 equals 16a plus, this term is 0, this would be c, this would be -1, so really minus c. Why is that nice? Well, because I already found a, I can now solve this equation for c really quickly. This says 17 equals 16 times 1 minus c, which is the same. If I subtract this 16 over, I get 1 equals -c. So c is -1. Sneaky, sneaky, right? And then lastly, maybe I'll plug in x equals +1, see what I get. So I don't want to crowd the page there. So let's plug x equals -1 here. Then I'll get 17 equals -1 squared is +1, so this would be 17a again, plus, if I plug in -1 for x, this will become -b plus c times -2. And since I know a and c, I can solve this equation for b. A is 1, so this says 17 equals 17 plus, c is -1, so this is -b minus 1 all times -2. Subtract the 17s, you get 0 equals -b minus 1 times -2. Divide the 2, and you get 0 equals -b minus 1. Add b, you get b equals -1. So without ever having to set up a system of equations, I'm able to recover a, b, and c here. It is kind of a modified form of the Heaviside trick. The Heaviside trick is awesome. It works really fast, but it doesn't always work. But the mechanics that underpin it are still useful, even in these more complicated setups. So we've been through a few problems like this, and I just wanted to show you these tricks at least once. couldn't resist. The complex numbers thing, if you want to play with that, see me in office hours. I don't want to overwhelm. But the upshot here is that my integral of 17 over x minus 1 times x squared plus 16 dx is equal to the integral of a over x minus 1, and a was 1, so that's 1 over x minus 1 plus bx plus c, that's negative x minus 1 over x squared plus 16. And the easiest way to attack this problem from here is to split into 3 integrals. So I'll have my integral dx over x minus 1. And then this guy I can split as negative x over x squared plus 16 minus 1 over x squared plus 16. All right? So that will be minus the integral of x over x squared plus 16 dx minus the integral of dx over x squared plus 16. Like so. The first guy is a little micro u sub. The second guy is a slightly less micro u sub. And the third guy is an inverse tangent function that you will either be comfortable with the formula that I showed you once, or you'd have to do some trig sub. Naz asks, could you use the PFD trick I used here on the test? Yeah, absolutely, by all means. Do whatever you can to solve the problems. I encourage you to stick with things that you're comfortable with, because correctness is more important than brevity. So worry about getting the thing correct before worrying about going fast. But if you are comfy with this trick, then yeah, by all means, use it. So this first guy, I'm going to make the substitution z equals x minus 1. dz is dx. The second guy, I'm going to make the substitution w equals x squared plus 16. dw is 2x dx. Make sure you're using different letters for these. And the last guy, I'll say maybe y. Oh no, this one's different. Yeah, this one is going to be x equals 4 tan theta. So dx is 4 secant squared theta d theta, like that. So that first integral becomes the integral of 1 over z. The second integral becomes 1/2 integral 1 over w. And the third integral becomes something really nice also. So that third guy is going to be 16 tan squared theta plus 16 downstairs, and 4 secant squared theta upstairs. Oh shit, I fucked that up, didn't I? I'll write it like this. There we go. So these should actually be written in the other order, but it's addition, it doesn't matter. I just wrote the plus sign without thinking. So this is going to be the natural log of the absolute value of z minus 1/2 natural log absolute value of w minus, I can factor a 16 out from the bottom, so you get 4 over 16, which is 1/4 integral secant squared theta over 1 plus tan squared theta d theta. But 1 plus tan squared is secant squared. This is minus 1/4 integral of just d theta. Of course, the natural log of z is the natural log of x minus 1 minus 1/2 ln w is ln x squared plus 16. So that's where we're at. And the integral of d theta is theta. So this is ln abs x minus 1 minus 1/2 ln abs x squared plus 16 minus 1/4 theta plus c. And then what is theta? Well, x over 4 is tan theta. So the inverse tangent of x over 4 is theta itself. So finally here we have ln x minus 1 minus 1/2 ln x squared plus 16 minus 1/4 inverse tangent x over 4 plus c. And that last integral, the one that really consumed the time there, the arctan integral, I recommend proving a formula that will allow you to solve those very, very quickly. I recommend proving that the integral of 1 over x squared plus a squared always comes out to 1 over a times the inverse tangent of x over a plus c. And I would be okay with you using that on a test. The same way that I'm okay with you like memorizing the integral of secant, I'm okay with you memorizing this integral if you want to. Best way to memorize it, go through the proof. It's not hard. Just substitute x equals a tan theta and follow your nose. It goes the same way as this integral did, just with an a instead of a 4. Okay, any questions on this guy? The PFD or any of the integration? Yeah, finding the coefficients can be a little bit tricky here. Because the Heaviside trick doesn't do everything for you, you need to do something else. The version of something else that I did here, not too bad. The alternate approach would be to multiply everything out and then equate coefficients on the left and right. So if you multiplied everything out in this line, and then set the coefficient of x squared on the left, which is 0, equal to the coefficient of x squared on the right, which is a plus b, then you would find that a plus b equals 0. And you do the same thing. I'm sorry, my cat is dancing, and it's hilarious. And you do the same thing for the other terms. I can walk you through that quickly. Here is the thing I was suggesting that you prove. The integral 1 over x squared plus a squared is 1 over a times the inverse tangent of x over a plus c. This is in your book as, I think, formula 17 in section 7.5. How's my memory? Boom, 17. All right, sorry. That was a small victory for me. Yeah, this is the formula, right? This guy. It's one of these like standard integrals that we want to know well. I say don't worry about 19 or 20, don't worry about 15 or 16, because those involve things that either like this you would want to work out, or like these, the hyperbolic trig functions, we don't really fuck with those too much in this class because those are all about complex numbers. But proving 17 is a good idea, and that is the formula that I have on the page there. So I want to, for those who are having a little bit of a hard time with the coefficients, I want to take this line here and show you the standard approach, right? So what we did there was a trick. The standard approach that would allow you to find these coefficients, no Heaviside trick, no nothing. You take your 17 equals, and then distribute all this shit out, multiply everything out. So this is ax squared plus 16a plus bx squared plus cx minus bx minus c. All right, so you distribute everything out, and then we're going to put all the x squareds together. We're going to put all the x's together, and we're going to put all the constants together. So that becomes 17 equals a plus b times x squared. And then c minus b times x. And then constants, we have 16a minus c. And then from here, you interpret the left-hand side as 0x squared plus 0x plus 17. And you set the coefficient of x squared on the left equal to the coefficient of x squared on the right. So that means I set this 0 equal to this a plus b. You set the coefficient of x on the left equal to the coefficient of x on the right. I'm going to write this as negative b plus c. And finally, you set the constant terms equal to each other. So you'll have 16a minus c equals 17. And I'm writing things like this because I'm thinking of it as a system of equations. You could think of this as a matrix if you wanted to, or you can solve it by elimination, you can solve it by substitution. It's all up to you. But from here, the game would be to solve this system, and that's how you get the coefficients. This is the surefire method. Right? If you remember, this is actually what we did the first few times we talked about PFD. We set up a system of linear equations that we then solved for A, B, and C. And this is what will always work. If you're not sure what else to do and you're looking for something that is like a straightforward algorithm that you can always run and will always work for you, this is it. The Heaviside method and these other tricks I've shown you are just tricks to speed up the process. So if I needed to solve that system, I would either think of it as the matrix 1, 1, 0, 0, 0, negative 1, 1, 0, 16, 0, negative 1, 17. So this is the augmented matrix for that system. And then row reduce. Not too hard. If you remember the game for solving systems or row reducing matrices, first you make this number a 1, and then you make everything beneath it 0. Then you make this number a 1 and make everything above and beneath it 0. Then you make this number a 1 and make everything above him 0. This guy, my first pivot, is already a 1. So in order to get rid of this 16 down here, I multiply row 1 by negative 16 and add it to row 3. There is a notation for this I like. The new row 3 is equal to old row 3 plus negative 16 times old row 1. You write down the rows that don't change first. So 1, 1, 0, 0, 0, negative 1, 1, 0. And then negative 16 times 1 plus 16 is 0. That's by design. negative 16 times 1 plus 0 is negative 16. Negative 16 times 0 is 0, so this guy stays a negative 1. And negative 16 times 0 is 0, so this stays a 17. And that's my first row operation. Now column 1 is done. My next step would be to make the pivot in column 2 equal 1. So I would multiply through row 2 by negative 1. So my new row 2 is equal to negative 1 times my old row 2. Rows 1 and 3 don't change. So we copy those down first. And row 2, I just flip the sign. So that's 0, 1, negative 1, 0 now. Then I need to clear everything out above and below here. This process takes a little bit of time. This is why I don't usually recommend it. That's why we have the tricks. So if I want to clear out this negative 16, I'm going to multiply row 2 by 16 and add it to row 3. In other words, my new row 3 is my old row 3 plus 16 times old row 2. Rows 1 and 2 don't change, so I leave them. Row 3 is being changed here. This guy stays 0. 16 times 1 plus negative 16 is 0. That's by design. 16 times negative 1 is negative 16. Negative 16 minus 1 is negative 17. And 0 times 16 is 0, so this stays a 17. And now our matrix is in, it's called echelon form. It's not reduced row echelon form, it's just row echelon form. So I can take it back to a system now and back substitute. So this is the same as saying A plus B equals 0. B minus C equals 0. And negative 17C, this is the good news, equals 17. Once you're in this reduced form, where you've got zeros below the main diagonal, then you can always solve for this last guy. So this equation tells me that C is negative 1. And then I back substitute that here. So B minus negative 1 equals 0. So B is negative 1. And then finally, A plus B equals 0. So A plus negative 1 equals 0. So A is positive 1. This is the long way to do it, right? And I haven't done one of these out where we put it into a matrix and row reduce the matrix yet. So I'm happy to do this, especially since I know not everybody gets a good treatment of linear algebra in their pre-calc class. But this is the game. So the matrices are just one way to solve a system like this. I would never say you must use matrices to do this, but you must have some mechanism for solving linear systems. Matrices, I think, are the nicest, cleanest way to do it if you're looking for a direct procedure, right, rather than using a trick like the Heaviside trick. But no, if you preferred to use elimination or substitution, you would be welcome to do that also. However, linear algebra is kind of the best shit in the world. In some very meaningful ways, matrices are the most important mathematical objects on the planet. So I recommend getting comfy with it. But of course, right now you guys are all worrying about exam 1 and you want everything to go well. So, you know, please don't panic. If you hate matrices right now, then you don't have to use them. Yeah, so reducing 4x4s and 5x5s by hand is horribly unpleasant. The reason matrices are so awesome is not because row reduction is fun. It's all about the theory that underpins them, called linear algebra. Without linear algebra, there is no PFD, not just for this reason, but because the vector space theory is what guarantees the existence of the numbers A, B, and C. Yeah, it's good stuff. But row reducing, I acknowledge, sucks. If you want to do something else, do something else. My suggestion is to use the heaviside trick to get as much out as you can. And that way you should never have to solve a big system by hand. Okay, that's enough time on this problem. What else would we like to do? Did we have other requests in the chat? We had some study guide problems, right? 8 from the study guide, 9 from the study guide, and some trig integrals we wanted to look at. Okay, let's look at 8 and 9 from the study guide. This is the homework. So Ryan asks, when we found the number B in that PFD, did I pick any number? So the first approach, when we went through that the first time, the way I found the coefficient B here was by plugging in x equals -1. Yeah, I just picked a number at random that I thought wouldn't be horrible to plug in to this expression. Plugging in 1 is an obvious choice because it makes this factor 0, so I know that will give me A immediately. And then plugging in 0 and 1, those were arbitrary choices that I made. They're just numbers that I'm not afraid to plug in. They're like easy to work with, that's all. Okay, so 8 and 9 from the study guide were the first ones that were requested here. So let's take a look at those, and then we can do some other problems. There will be office hours today. Yep, I'll have my normal office hour from 1 to 2. So 8 is a good trig integral. We'll write this down and we'll come back to the dot cam. Looks like this. So we need to think about our strategies for secant tangent integrals. So remember, if the power of secant is even, then we can pull 2 copies of secant off to the side, rewrite the remaining secants as tangents, and then substitute for tangent. Or if the power of tangent is odd, we can pull a secant tangent off to the side, write the remaining tangents as secants, and substitute for secant. So this is an integral that can be done 2 ways. And you have to pick a strategy at the start. We're either going to sub z equals secant x, or we're going to try to sub z equals tangent x. If we wanted to substitute for the secant, then I grab a copy of secant tangent and set it off to the side. So that will leave me 2 tangents here, 5 secants here, and then I have secant x tangent x dx that I'm setting aside for my differential. If I aim to sub for tangent, then I set aside 2 copies of secant. So that leaves me tan cubed x, secant to the 4x, secant squared x dx. Before I'm able to implement either of those substitutions, though, I need to rewrite the remaining powers of the other trig function in terms of the one I'm going to substitute for. This, to me, makes the secant substitution look nicer. Tangent squared can be written as secant squared minus 1 and over here, secant to the 4 can be written as secant squared squared. So this is secant squared all squared. And then secant squared is tan squared plus 1. Right? So now we're ready for our substitutions. I like this one more because it doesn't involve foiling out any algebraic expression. But here, if I let z be secant x, dz is secant x times tangent x dx. So this integral will become z squared minus 1 times z to the 5 dz, which is a polynomial integral. We can handle it, it's not bad. And it's especially nice because I don't have to multiply anything out. So this is integral z to the 7 minus z to the 5 dz, which would become z to the 8 over 8 minus z to the 6 over 6 plus a constant. And then we go back to our secants. So this is secant to the 8 of x over 8 minus secant to the 6 of x over 6 plus c. All right, that's one solution. The other guy, if I sub, I'll use a different letter here so things don't get confused. W equals tan x, then dw is secant squared x dx, and my integral becomes w cubed times w squared plus 1 quantity squared dw. And this is also a polynomial, but it's not as easy to integrate as this because I have to FOIL that out before I distribute it. And in theory, if this power were like 20 instead of 2, then I would have to FOIL out the 20th power of that binomial, you know, which can go to hell. I don't want to do that. Even with the binomial theorem, I don't want to do that. But here, this one's not unmanageable. There's the foiling. Then we distribute. And then the integration step. This would be 2/6 or w to the 6 over 3. And then we plug back in for our trig function, which is tangent. And you get these two very different looking answers. But if you play around with trig identities, you'll see that these are either exactly equal to each other or equal to each other plus or minus some constant, like 1 or 1/5 or 2/3 or something. The vertical translates of each other. And that's to be expected because the indefinite integral, remember, isn't one function, it's an infinite family of functions. That's the whole plus c thing. So either one of these would be correct. I know which one I would want to do. because this guy is more algebra. All right, any questions on this problem? This is a fun one. I'm glad we came back to trig integral land for a minute. It's good stuff. If you don't remember those strategies, you may want to go back and remind yourself. Sine cosine integrals, we break down into 2 cases. Secant tangent integrals, we break down into 3 cases. The sine cosine integrals, if there's any odd power, are easy. We just substitute. You grab a copy of the other guy, rewrite everything else in terms of the first, and then substitute for the first. If both of the powers in the sine cosine integrals are even, then you got to beat them to death with those half angle identities. And then the secant tangent integrals, if the power of secant is even, you can try substituting for tangent. If the power of tangent is odd, you can try substituting for secant. And then if you're in the nasty case where the power of secant is odd and the power of tangent is even, then you're setting up for some looping IBP. And so I don't want to call anybody out, but if you guys see what Nick is talking about in the chat, I bet it's a mistake that a lot of people would make, wanting to distribute the w squared over the w squared plus 1, or sorry, the w cubed over the w cubed plus 1 before foiling. This is why I really prefer this path. The less room you give yourself to make little errors, the less likely you bump into one of those little errors. And most of the mistakes in Calc 2, small algebra mistakes that then follow you through the rest of the problem like a nightmare. So try to set yourself up for the easiest path. And then also move slow, right? I know I tend to move a little bit fast through these problems when we do them here because there's this time constraint. But as you work the problems in homework, go slowly. Take your time and be very, very careful. We want to train you guys to be exceptionally careful with your mathematics. Okay. I think that's enough time on this guy. We've got time to do one more. So let's come back here. This was 8 from the study guide, 10 from the homework, 10 from the study guide, 7 from the study guide, 8 from the study guide. Okay, let's take a quick look at 7 and 10 in the study guide. We'll pick one of them. Yeah, that shit happens. Mistakes like that are not uncommon. You guys have seen me make mistakes like that, but if you go nice and slow, you can minimize them. So 7 and 10 were the other 2 requested from the study guide. 10 is pretty quick. What about 7? What is 7? Ooh, 7 is looping IVP. Is there time? All right. Tell you what, I'll show you 10, and then I'll get you started on 7. I want paper too. All right. I'm a fan of problems like this. And in fact, there are some more complicated problems of this nature that I also really like for test problems, where you need to make a little substitution and then you get a rational function. Sometimes you can make a little substitution and then set up some PFD, stuff like that. Here, the rational function we're going to have after our substitution is made is simple enough that it won't require any partial fractions. So I'll begin by popping out the 5. I'll leave the denominator alone. But if you look at the numerator, e to the 2x, that's the same as e to the x squared, like this. And an important note, e to the x squared, like this, always means e to the x times e to the x, which is e to the 2x. E to the x squared without parentheses always means e to the parentheses x squared, like this, which is very, very different from e to the 2x. So this is a notation thing. When you see e to the x squared on the bottom, remember that it's really like this. And anytime you need to write the square of e to the x, you should write it like this or just as e to the 2x. So yeah, just be careful with the notation there. It's a standard kind of convention. This function is actually hard to integrate. He doesn't have an antiderivative that can be expressed in finite steps. I will show you how to find an antiderivative for him later, but we'll need what are called power series to do it. From here, I think we should be able to see what the move is if I write it as this, then the natural move is to sub for e to the x. You could also sub for the denominator. But what feels more natural to me is letting z be e to the x, dz is then e to the x dx. So this would become 5 integral z over 7 plus z dz. And then how do I handle that integral on the bottom? So another substitution actually won't do it. Or maybe it could be done with another substitution. I argue that there's a more natural thing to do here. This is a rational function where the degree of the top is not strictly smaller than the degree of the bottom. So you should long divide. I can't split up the fraction over its denominator. So the suggestion there that we try writing z over 7 plus z as z over 7 plus z over z. This is actually not kosher, and it's a common mistake, so I'm glad that it's brought up. Fractions, you can split them up over their tops, but we can't split them up over their bottom. Simon's suggestion in chat would work. If we came back to this step and substituted for 7 plus e to the x instead, we could make that go, and that will work just fine. But you will need to solve your substitution for e to the x in order to write the numerator, because you have this piece left over. It works fine. It will come out as z minus 7, and that works great. However, I contend that this is a bit more natural, and I also feel like we should know what to do with this. So I want to hang out on this for a second. We have one suggestion so far, but the algebra won't work, so we can't do it like that. Right, this stuff doesn't work. The underlying rule here is that a plus b over c is a over c plus b over c, but a over b plus c is not a over b plus a over c. So we can't do that. But instead of that, IBP might work, but it's definitely overkill. I don't see a natural way to split this as u times dv. Certainly not one that would yield something nice. It's true, it's true. There's nothing wrong with going back and making that other substitution. But yes, there we go, long division. That's the thing. This is an improper rational function. The degree of the top is 1, the degree of the bottom is 1. You need to long divide. It will work. So we're going to long divide z by I'm going to write that denominator as z plus 7. So by what must I multiply this in order to get this? 1. Distribute the 1. Subtract. Z minus z is 0, and this is z plus 0. So 0 minus 7 is minus 7, which tells you that z over z plus 7 is equal to 1 minus 7 over z plus 7. That's it. So my integral, all this stuff tucked in a box, my integral is equal to 5 times the integral of 1 minus 7 over z plus 7 dz. Now this guy is a micro u sub for z plus 7, so this is 5 times z minus 7 ln absolute z plus 7 plus c. Distribute the 5 and go back to our substitution. We get 5 e to the x minus 35 natural log abs e to the x plus 7 plus c. I contend that this is the most natural path. At no stage here do you need a hard-to-spot substitution, and the resulting integral, if you just follow the natural discussion from section 7.4 on integration of rational functions, since this is a rational function that is improper, we long divide, and the result drops out nice and quick. I'm not writing the micro u sub for this because I'm lazy, but that's it. Simon asks an interesting question. Can we long divide with the e to the x? Yeah. So the rules that make long division work are specific to polynomials. And e to the x is not a polynomial. So see, so there's no point in writing z equals 0. So, yeah, that wouldn't, so rewriting 7 over z plus 7, without parentheses, it's a little hard for me to, as a over z plus 7. Yeah, so Naz, I think I understand what you're asking. You're asking, would it be worthwhile to try setting up partial fractions for this? The answer to that is no, because the rational function that you get after your substitution is improper. So PFD only works for proper rational functions, which this would not be. Quick answers to remaining questions. There's a faster way to do this long division. I call it the add and subtract trick, or poor man's long division. Since I'm sick of seeing z's and 7's in the same place, I'm going to just switch the variable here to x. Quicker way to do that long division? This is totally kosher. I just added 0 to the numerator. And now if you regroup, that's x plus 7 over x plus 7 minus 7 over x plus 7 dx, which is 1 minus 7 over x plus 7. So you can get there faster using this add and subtract trick. And it's basically the way you do the thing that we're tempted to do, right? You're tempted to split this up over its denominator and call it x over x plus x over 7, but that shit don't work. 1/2 is not 1 plus 1. But adding and subtracting in the numerator so that you can then group and split, this does work. It's nice. So my calc professor called this poor man's long division, and I like that. It doesn't always work. It works great with linear function over linear function. So there, in those instances, you can save yourself having to write down the long division if you use this add and subtract trick. I do think that's time for today. So I am going to switch over to office hours. If you guys want to work some more problems or talk about other stuff, just head over to the office hour link in Canvas. It's on the main page there in Canvas as soon as you click on our Canvas class. It's also on the syllabus page. So yeah, I'll see you guys there. Please watch over the weekend for an announcement with very careful, detailed instructions on exactly how to take the exam on Monday. Remember, it will be in Canvas rather than in WebAssign. So the procedures are changing a little bit, but just a little bit. And if you have any accommodations set up through the DRC, please reach out to Karma and reschedule the test. Talk to me. We're going to have to figure something out because Zoom proctoring might not be an option. Yeah, Nick, and anybody, if you want some feedback on the study guide, I strongly encourage it. Send it to me, and at some point over the weekend, I'll try to get to it as soon as I can. I will look through and give you some pointers, let you know if there's anything that is troubling or anything like that. Alrighty, any last minute questions before we move over to the office hour meeting? Yeah, you're a good kitty. All right, then I'm going to go ahead and end this. Oh, I see. Sorry. Oh, yeah, of course, no problem. All right, so I'm going to go ahead and end this meeting. If you want to talk more, come over to the office hour. Otherwise, send me any questions you have via email or Canvas messages. I'll get back as soon as I can. And good luck on the test on Monday.